Welcome to Mrs. Lee's Chemistry Academy. Today we're going to talk about solution equilibrium and factors affecting solubility. Tying to learning objectives from the College Board, the student can draw and/or interpret representations of solutions that show the interactions between the solute and solvent. Student able to create or interpret representations that link the concept of molarity with particle views of solutions. Student able to explain observation regarding solubility of ionic solid and molecule in water and other solvents on the basis of particle views that include intermolecular interactions and entropic effects. Now, here's a diagram showing the dissolving of sodium chloride in water. As you can see, there's sodium chloride ions or ionic solids sitting at the bottom of the beaker. As they become dissolved, the ions are formed, and then they become surrounded by water molecules. Chloride surrounded by the positive end of water molecules, and sodium, the cation, is surrounded by the negative end of water molecules. Now, as the concentration increases, these ions would then have a chance to recrystallize back into solid NaCl. And when the rate of dissolving is equal to the rate of recrystallization, a dynamic equilibrium is reached and a saturated solution is formed. There are several factors that affect solubility, one being polarity of molecules, like dissolves in light. Now, if you answer an exam question and you say light dissolves in light, you're not going to get any point for it. We really need to talk about the energy involved. Polar solvent water tends to dissolve polar or ionic solutes because the attraction between water and the ions are greater than the attraction between water molecules or the attraction between the ions themselves. Nonpolar solvents, such as hexane, tend to dissolve nonpolar solutes such as iodine. And again here, the energy involved is the attraction between hexane and iodine through this London dispersion force is greater than the attraction between hexane molecules or the attraction between iodine molecules. So here's practice problem 1. Draw a diagram to represent effective interaction between sodium ion, ethanol, dimethyl ketone, pentane being the solute, and the solvents are water, heptane, and chloroform. Now, if we analyze one pair at a time, the nonpolar pentane C5H12 will dissolve well in the nonpolar solvent pentane C7H16 because they both have London dispersion forces being nonpolar. The polar ketone will dissolve very well in the polar chloroform because there's attraction through dipole-dipole forces. Then finally, the ethanol will dissolve well in water because of attraction through hydrogen bonding. And then the sodium ion will dissolve well in water through ion dipole attraction. So the next slide will show the drawing of these attractions. Looking further to the left, heptane is attracted to pentane through London dispersion forces, represented by red dotted lines. The acetone is attracted to chloroform and dissolves well in chloroform through dipole-dipole force. Ethanol alcohol is dissolved in water through hydrogen bonding, and the sodium ion dissolves well in water through ion dipole attraction. Explain why oil grease on clothing cannot be rinsed off with water, and we all know that as a fact, but why not? Because the oil is made up of nonpolar hydrocarbon molecules with dispersion forces, and water is polar, held together by hydrogen bonding. It means that dispersion forces among oil molecules or the hydrogen bonding among the water molecules are actually stronger than the attraction between the nonpolar oil and polar water molecules. Therefore, oil cannot dissolve in water and cannot be rinsed off with water. The factors affecting solubility, second one is temperature. Here, look at this diagram of solubility of grams of solute in 100 grams of solvent water versus temperature. As you can see, most of them have a positive slope going up as temperature increases, solubility increases, but with sodium chloride it's a little bit flat. When we have a point, any point along that curve, on that curve, we call that a saturated solution, meaning the maximum amount of solute a solvent can hold at that particular given temperature. If it is a point below the curve, meaning it is an unsaturated solution, meaning more solute can still be added to the solvent. And if it is a point above the curve, it is a supersaturated solution, meaning that now the solvent is holding more than what it's supposed to hold. Solubility increases with increasing temperature for solids. Now, you might have seen a demonstration in the classroom by your teacher that a supersaturated sodium acetate solution has been prepared by dissolving a lot of the crystals in water at high temperature. Now, I will leave it untouched, and then slowly the temperature will cool down to room temperature. If we leave it untouched, it's all right. It looks like as if it dissolved. But the moment you add a small amount, a grain crystal of sodium acetate, the whole thing will precipitate out like an iceberg. It's really interesting to watch. Solubility of gas. Opposite to the solubility of solid, the gas actually decreases in solubility with increasing temperature. Because as temperature increases, gas molecules have greater kinetic energy and tend to break away from the attractive forces held by liquid molecules. That's why in the summertime, the fish will be found in the cooler region of the water rather than the sunny water, because it's too hot there, and it's not because the fish are afraid being hot. There's not enough oxygen for them to take in. Now, solubility of gases in liquid also increases with increasing pressure. And I think this following diagram will explain why. Initially, you have an equilibrium situation between the gas and the liquid. Now, as we increase the pressure and the volume becomes smaller and smaller, that's pushing more of the gas molecule, like CO2, into the water to form a solution. So solubility would increase with increasing pressure. Now remember when you take out a soda can of Coke from the fridge and you open the tap at room temperature and you hear the fizzing sound, that's because of the CO2 gas becoming undissolved from the water. When we express solution concentration, we can say it is very concentrated. That means it contains a large quantity of solute relative to the solvent. Or we would say it is dilute because it contains small amount of solute per given amount of solvent. We use molarity as the most common way to express solution concentration, which is defined as mole of solute per liter of solution, represented by the capital letter M. Molarity varies with temperature because volume is dependent on temperature. So when temperature increases, volume will increase and your molarity will decrease. Other expressions include molality, mass percent, parts per million or parts per billion, and mole fraction, but it is not used in the context of AP Chem, other than mass percent sometimes. Now, how do you prepare a solution? Calculate the mass of solute required to make a solution of known molarity and weigh it out. Then, transfer the solute to a volumetric flask on which the calculation is based. 1 liter, 500 ml, 250 ml, 100 ml, 50 ml, etc. Then you add distilled water to the flask, half fill, swirl to dissolve the solute. Then you mix it up to the mark, to the calibration mark, with more distilled water carefully. Make sure that you don't run over the line. Then you stopper and you invert and mix it several times, and then you label the solution. So here's a diagram showing the process of how a solution of given molarity can be made. To sum up what we have learned today, students have learned representation and explanation of interaction between solute and solvent. Students have learned the effects of molecular structure, meaning polarity, temperature, and pressure on solubility. We learned how to express concentration of solution in terms of molarity and the technique used in preparing a solution. From the team of MLCA, we would like to thank you for watching the video, and we look forward to seeing you again next time.